Hey, hi there. In today's video, we'll be exploring the probability distributions in Python. Okay, so whatever distributions we have learned in our PPT or slide, first we'll try to cover the discrete distributions, especially binomial and Poisson. But before that, we'll try to just do a quick recap of joint probabilities and what it means in Python. So let's first import all the necessary libraries. Now let's try to look at first joint probability. So let's look at the first question. So the first question basically gives you a cross table of the two basically attributes where people who have placed an order for Apple iPhone and people who have not placed an order for Apple iPhone, because here the condition is no, right? So calculate the joint probability people who plan to purchase and actually placed an order. So plan to purchase, here you can see here it is yes, who have planned to purchase and actually placed an order. So probably we have to search in this row, and in this row who have actually placed an order is 400, right? So 400 out of total, how much it is? 2000. So 400 of 2000 will be my probability of people who plan to purchase and actually placed an order for an iPhone, which is 20%. Correct? 0.2, which is means 20% probability. Next, we have conditional probability. Conditional probability is something which I've already talked about in conditional probability, which means that one event is dependent on the other event, right? That is why we have probability such that A such that B has happened, right? And a question based on that will be use the purchase of Apple iPhone X Max table to find the joint probability of people who plan to purchase and actually place an order, given that people plan to purchase. So given that people had planned to purchase, give the probability of people who plan to purchase and actually place an order. So that quantity we have already understood, that is 400. But here they are saying, given that people have planned to purchase. So the first event, that's A, such that B has happened. So B is nothing but this event. People had planned to purchase. Right, so it will be no longer 400 out of 2000, it will be out of 400 out of 500, because this row total gives us those people who actually have planned to purchase the Apple iPhone. So it will be 400 by 500, which is 80% probability, 0.80. Okay. All right. Binomial distribution. Now let's go to the distribution part. So here you can follow different questions. Here you can see we did not use any special function for conditional probability or joint probability, of course, because here the questions are pretty straightforward. In machine learning algorithm, when you go to naive Bayes algorithm, we'll talk about the Bayes theorem in detail, but that will be in the machine learning course of Eduvision. So now let's move to the distributions, the binomial and the Poisson distributions. So first, let's take into account the binomial. So if you just need a recap, binomial distributions are a collection of Bernoulli distributions, and these Bernoulli distributions have only two outcomes, a yes or a no. Okay, and when the number of trials increases, from one to many, that becomes a binomial. So a binomial is nothing but a couple of multiple trials of Bernoullis, right? So, and we also, if you do not even remember a formula, it's fine, right? But because Python has its own inbuilt function, but just to give a recap, and say x, p to the power x, 1 minus p to the power of n minus x. So x is the possible outcome, the probability of the possible outcome which we're trying to find out, p of x. If x equal to 0, this will become 0. N represents number of trials, p represents the number of the probability of the success. What chance are you looking for, right? And 1 minus p already know, and n minus x is something which you can easily derive if you know what is x and n. So let's take an example, and this is the example which we have already covered in our slides. And there we had used this formula. We draw the probability distribution curve. You can refer back to the slide if you want to in the previous video, right? So a bank issues credit cards to customers under the scheme of MasterCard. Based on the past data, the bank has found that 60% of all accounts pay on the following bill. If a sample of 7 accounts is selected at random from the current database, construct a binomial distribution curve or binomial probability distribution of accounts paying on time. So accounts paying on time is the success event, right? So success criteria. So here my P will be actually 60%. If the question would have asked distribution of accounts not paying on time, then my P would be 1 minus 60%, which is 0.4. But here it will be 60% because 60% accounts pay on time and 60% and the accounts paying on time is what is being asked to you. So my P will be 60%, 0.6. Number of trials will be 7. And the events, the possible events which will take, obviously out of 7 accounts, 8 accounts cannot pay on time, right? Either 0 accounts will pay on time, 1 account will pay on time, 2, 3, 4, 5, 6 till 7. So range of 0, n plus 1. N is already 7. So 0 to 8 will give me 0, 1, 2, 3, 4, 5, 6, 7. That will be my value of K. So once I've defined the events, I'm asked to draw the entire probability distribution. So basically what they're trying to ask me is to plot the possible events on the x-axis 0 to 7 and its corresponding probabilities based on the binomial distribution formula. But you don't even remember any formula. We have a function called binom.pf. Now if you PMF, now if you go up, I've imported the function, or maybe I imported here, yes, from scipy. So scipy is the module which allows you to use probability distributions directly, statistical probability distributions directly, right? So from scipy, import stats as st. That is what I have done. And inside these st or stats module, we'll have all these Poisson, binom functions and everything, normal distributions and everything. Z, even the hypothesis testing, while doing a hypothesis testing, we'll also import all these functions from a similar library. Right? So from scipy, import stats as st, n equal to 7, k is equal to range of 0 to n plus 1, and p is equal to 0.6. Now, once we have this, we use a function which is called as, from stats module, st.binom.pmf. Binom means binomial distribution. .pmf means probability mass function. Probability mass function is a plot between the number of events, between the events on the x-axis and its corresponding probability on the y-axis. There is one more function in binom which is called as CDF. CDF means the cumulative probabilities on the y-axis and the events on the x-axis. So here the graph will be somewhat like this probably, okay? Here it is cumulative, so it will keep on continuously increasing till we reach the total probability to be 1, right? But here I'm going to plot the probability mass function, not the CDF as of now, okay? Let's see. Now this PMF function requires 3 parameters. What are the 3 parameters? K, N, and P. Now if you remember, number of trials and probability was the parameter of a binomial distribution, right? K means the number of events. Okay, if you put one single event, it will give you 1 probability. If you give a range of events or multiple events, it will give you multiple corresponding probabilities. Very simple. Okay, so you can take either one single value of an indication of an event. So suppose if I want to find out the probability of 0 accounts paying on time, then K will become 0, number of trials is 7, P is 0.6. That's it. But if I want to find out, say, if I want to construct the entire probability distribution table, then I'll put the entire list of 0 to 7 in this particular value of K, and then, number of trials and 0.6, whatever it is, P. So you can take either one single value, it will give you one particular probability with respect to the particular event, or you can give a range of events and give you a range of probabilities directly with respect to each of these events. So what I'll do, I'll directly do that. I'll just simply put this range values here directly, comma n, comma p. I can see here, I have to run this first. And once I run this, you can see all the probability. So this is the probability of 0 accounts paying on time, 1 account paying on time, 2 account, 3 account, 4 account, 5 accounts, 6 accounts, 7 accounts paying on time. Right? Now, if I want to simply plot the distribution curve, what I'll do, plt.bar, right? A bar plot simply. On the x-axis, there will be the values of K, y-axis, the corresponding probabilities. If I do this, you can easily get the bar plot of the, or a probability distribution graph of the binomial distribution determined by accounts paying on time. Right? So here, just if you do not want this object to be seen, I can simply do underscore equal to, or you can do plt.show. If you do that also, it will be removed out. You can also specify here p.x label. What does x label mean? Accounts paying on time, right? And y label, period y label is nothing but your probability. That's it. Very simple. So let me just make it real touch. And I'll remove this out. Great, isn't it? Right? So this is how we need to do it. And if I want to go back to the slide where I did that question, if you go to the previous video, this was the question, wasn't it? Right. And this is how we created the graph. By this using this formula, we got this all these corresponding probabilities with respect to each value of x, or I can call this k, whatever you call it. And then I do this. Correct? Okay. Okay. All right. So you can see manually takes so much time, there's so much effort to be done, right? In Python, it's just a matter of few lines of codes. That's it. Correct? So this is how Python helps you. Don't remember anything. What you don't remember is the function, at least some idea about the function name. Even the parameters, what order it takes, you can easily Google it. No problem. Okay. All right. So question 3, let's take some more questions. LED bulb manufacturing company regularly conducts quality checks at specified periods on the products it manufactures. Historically, the failure rate for LED light bulbs that a company manufactures is 5%. So the failure rate is given to you. Suppose a random sample of 10 LED light bulbs is selected. What is the probability that none of the LED bulbs are defective? Exactly one of the LED bulbs is defective. So all of these questions, if you see, these are asked on the probability of it being defective. And the failure rate is also indicates defectiveness only. It's given as 5%. So here my P, the probability of success is actually 5%, because that is what actually is being asked to you. If the question would have asked about non-defective, then my P value would be 95%. Okay, so please be very careful. Whatever is being asked in the question, what is the solve problem statement? What is the problem statement that you are solving will be the value of P. Okay, so P is 0.05 here, 5% is 0.05. We have 10 LED bulbs. So out of 10 LED bulbs, 11 LED bulbs cannot be defective. So we'll take from 0 to 10 plus 1, 0 to n plus 1, which is 11, right? N is 10, number of trials. Here also same way, st.bynum.pmf of k, n, p. Very simple. This is my entire list of probabilities. And if I want to plot, I can simply copy, paste the entire code from here. And this will be number of defective bulbs. That's it. This is probability. This is the probability distribution of defective bulbs, right? But what is the question being asked? Here, they have not asked us to plot the distribution curve. They have asked us to find out that none of the LED bulbs are defective. Now here, what does these probabilities refer to? This probability refers to k equal to 0, k equal to 1, k equal to 10. So the first probability is nothing but 0 probability. So the index, I can simply say probs of 0. It'll give me 0 bulbs defective. Probability of 0 bulbs defective. Probability of 1 bulbs defective. So prob 2 or fewer. 2 or fewer means what? 2 or fewer. Right? So here we have 2 or fewer. So 0, 1, or 2. So these 3. So I can simply make it as 0, 2, 3 dot sum. That's it. Yes or no? First, you have to understand exactly what this is giving us, and then you have to solve it. 3 or more. Now tell me, 3 or more. Which one will it be? 3 or more. So this is 0, 1, 2, 3. 3 or more. So from here to here dot sum. So 3 is 2 dot sum. Cumulative probabilities, because they are asking 3 or more than bulbs. Total probability of 3 or more bulbs being defective. Right? So this, or you can subtract the previous question, the previous probability from 1. Same thing. 2 or less, 3 or more. 2 or less, we have already found out. We can subtract 2 or less from 1 to get 3 or more. Very simple. Previous question was so 0, 1, 2, 3, dot, 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 till 10, right? So this probability we have already found out. Next question they're asking, because this is discrete. There can be no events between 2 and 3, right? So next is this. All I have to do is simply subtract this particular probability from 1 to get this. Right? Same way. Okay. Now you can plot the distribution curve. So I'll just remove it from here because I'm already plotting it below. If I want to plot the distribution function on a PMF, I can simply do this. Number of defective budgets. Okay. You can also plot a CDF. CDF also requires the same parameters K and P. Just that instead of PMF, this will become CDF, cumulative distribution function. It's not called as cumulative mass function. Huh? It's called cumulative distribution function. Okay. For discrete random variables, we call it as probability mass function, and the cumulative is called as cumulative density function. However, for continuous distribution, this is for discrete. For continuous distribution, we call it as PDF and CDF distribution function. Just remember this, guys. Okay. Cumulative KDB. If you want to plot it, I told you the probabilities will keep on increasing, right? Because it's cumulative. And when this is basically your cumulative, right? Now, if you want to compare with the individual probabilities, let's check what happens. This is 0.598, right? This is 0.5. The first one will be the same. Second one will be the addition of the previous and the present probability. So 0.59 plus 0.315, okay, all right, will somewhat lead to 0.91, right? Correct. 59 plus 31 is almost 90, correct? 91. So again, this will be 51, 59, 31 and 0.7, right? So again, it will be 0.98, right? So this is how it moves. Okay. So this is how the cumulative probability works. 0.5, 0.31, 0.59, by the way, this is 0.007. So this too is 0.91. This is again here. So this will be 0.98. Again, this will be added with this to give this. Right. So this is how it works. Okay. So if I find out this probability is nothing but the probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. That is what it means. Okay. This will mean again plus probability of x equal to 3 because this is cumulative, whereas this is individual. Probability of x equal to 0, this is probability x equal to 1, this is probability x equal to 2, individual probabilities. But here it is all cumulative. Okay. And that's why you can see here at one point of time, there'll be not much change in the total probabilities because the individual probability is very, very less, right? You can see here the individual probabilities are very less. That's why not much difference in the graph's height, right? Total probability is always, sum of total probability is always 1. All right. So let's go to now Poisson distribution. We'll know what Poisson is. There is one parameter which is called as lambda. Okay. Let's see. Let's pick up my question. The question which I'll pick up will be from the slide. Okay, the first question. Customers arrive at a rate of 72 per hour to my shop. What is the probability of K customers arriving in 4 minutes? K customers arriving in 4 minutes. So 4 minutes is my interval. So I have to convert this 72 per hour to some value per 4 minutes. I've already explained this in the previous video when I was explaining the slide, right? Theoretical part. So it will be 72 divided by 60 will give us minutes into 4 will give me that quantity per 4 minutes. So it will be lambda will be 4.8 customers per 4 minutes. Okay. All right. So now the question is, now let's first look at the plot the probability distribution function. Then we'll solve all these individual questions, which are very easy. Okay. So now how many such customers will I account for? because here we do not have a particular number of trials, right? So I'll be picking up say 17 customers, still 17 customers. K is equal to range of 18 will be from 0 to 17. So similarly, just like binom, we have Poisson. POI capital double S O N. POI double S O N dot PMF. Here, unlike in binomial, we have three parameters K and P. Here we have K and lambda. Okay. K is again the entire range of the possible number of events. Once we get all these probabilities, I can simply use a bar plot to express the probability distribution graph for this Poisson data. Okay, so customers, you can call it as number of customers here. Yeah. Okay. Okay, so let's now go to the slide and try to see where it was. So this was the question, right? Correct. And we had to calculate this using this formula. Next, we use this formula to create this table of the events and its corresponding probabilities, and then plot the distribution graph, right? But here it is very simple. You can directly use a single function to calculate all the probabilities and then plot it against the number of events to get the bar diagram. This is your probability distribution graph. Very simple, right? So there's one more question, right? This was the question. Okay. So I work as a data analyst in Edividend Private Limited. After analyzing data, I make reports where I have efficiency of entering 77 words per minute with 6 errors per hour. What's the probability that I'll commit 2 errors in a 455 word financial report? So lambda underscore will be same way which I had done here, explained it, right? I have to convert these words per minute and errors per hour to errors per word, right? So 6 errors per hour divided by 77 words per minute. So minute I have converted to hours, okay, and then multiplied by 455. So if I do this, so that will give me in 455 number of words, 0.59. So this is 0.59 errors per 455 words. Okay. Now question is asking that will commit 2 errors. So as I told you, just like in binom, my K value or K parameter can be a single digit or number, or it can be an array of numbers. If you put a single digit, it will give you the probability with respect to that number of event, or if you put in an array, it will give you all the probabilities with respect to all the numbers in those arrays or the events in those arrays. So here the event is 2 errors. So directly I'm putting 2 here, comma lambda. So this will actually give me the probability, directly the probability of committing 2 errors in 455 word financial report, which is 9.67%. Okay, I'm multiplying by 100. So this will be in percentage. And if you go back to the slide, the same answer, 9.6%. Okay. Now remember in the second part, there's a question which said, let's calculate lambda with respect to 255, 455, and 1000 word intervals, and also plot the distribution graph as well, right? So how will I do it here? Very simple. Here it will be, would have been a very humongous calculations, because for each of these lambda values, I would have to calculate the the corresponding probabilities with respect to each of these events, 0 to whatever it is, right? For every value of lambda, and then do a group bar plot, right? So instead of doing this, so these are the 3 equations, right? 3 probability distributions, right? So here I can do it very quickly. So simply st.poisson.pmf, k comma lambda underscore 1, k comma lambda underscore 2, k comma lambda underscore 3. So k I've taken till 0 to 8. So similarly here also I've taken till 7, right? So 0 to 8 here means it will run from 0 to actually 7, right? Because we all know in range function, the last digit which you specify, the ending index which you specify, the ending number which you specify is not taken, right? One less than that is taken. So that is how it works. So these are the distributions or probability distributions for each of these value of lambda. So now what I'll do here, sorry, I have to first calculate this. So since I know the calculation of previous lambda, I can simply multiply it by the respective number of interval width which I want. Okay. Now, once I've done this, once I've got all the probabilities, I can create a data frame out of these probabilities, right? Be the data frame of these values. I just want to show you one thing. Please understand, from pandas.plot, if you remember, in order for me to create group bar plot, right? I need the data frame with say x1, x2, x3, and the grouping with respect to what grouping we do should be set as an index, right? So that index will be my event, which is 0, 1, 2, 3, whatever it is. So ultimately, first I need to create a data frame for me to plot a group bar plot, right? So data frame of, let's say I'm putting k, I need k also, right? And probs 1, probs 2, probs 3. These are simple things which I've already done before, guys. Okay, but still I'm repeating it for your sake. I don't want it in this way. I want it in the vertical way, of course. Transpose. Now I have this. Okay, this is our k values. These are the probabilities with respect to lambda 1, with respect to lambda 2, with respect to lambda 3. That's why I'm specifying all the column names here. Okay, right? So once I do this, let's look at the k value. This is lambda is equal to 0.33. 255 words के लिए है. This is 455 words. This is 1000 words. Ultimately, this is probability, guys. Okay, this is probability only. Just with respect to lambda, which is 0.33. Okay. So once I have that, right? So now I'll set this k value as an index for me to draw a group bar plot. Once this becomes an index, now if I do d underscore dot plot kind is equal to bar, what will happen is it will group this entire these three values with respect to 0, and it will draw the bar diagram for each of these respective values of probability. See, with this to 0, 0.7, then this 0.5, then 0.2. Correct? The same graph which we had here. Very easily, right? I can also do plt dot say x label is nothing but my number of errors. Okay, and plt dot y label will be probability. Very simple, nothing but probability. And plt dot show. Okay, because when you do group bar plot, the column name itself becomes the legend. That's why I'm using it like this. So these small things, guys, will help you in solving problems more quickly. Okay, because if you want to create a group bar from scratch in scatterplot, it's not that easy. So you can use a pandas plot directly by simply setting the grouping criteria as an index, right? The grouping criteria here is that what? The event, and can set that event or k, whatever it is, as an index. Okay. Let us take another example now. A life insurance agent sells on average 3 life insurance policies per week. Use the Poisson law to calculate the probability that in a given week he will sell some policies or whatever policies. Ultimately, it is asking in a given week, and this is also per week. So my lambda itself directly is 3. So my lambda value is 3. So once my lambda value is 3, some policies means what? Greater than 0, right? And how many such how many such events will you take? Possible events 15, let's say 15, 16, 17, whatever you want to take. Okay, earlier I've taken 18, let me take 18 again, no problem, right? So once I specify the possible events, then lambda is 3 and x is 18. So this is the probability distribution. This will be ST, sorry, table. Probability table, right? But they have not directly asked about all this now. They have asked a particular question, right? What does the question indicate? I can simply calculate so that I can directly, from that probability distribution array, I can calculate all the respective probabilities with respect to the events which are being asked. Either way, or you can directly put that event which has been asked into the function. Okay. let's do the way we have been doing so far. Put the value of X, put the value of lambda, get the probability distribution, right? And then you can answer the questions. What is the first question? Some policies. Some policies will be, this is for 0 policies. This is 1 policy. So from 1 onwards, you have to sum up all the probabilities. See, P of 1:2 dot sum. Done. Okay. Or I can directly put it directly inside the function. See, instead of X, I'll say 1:, whatever it is, 18, right? Total, and do dot sum. Oh, this will be comma, na? Same thing, no? This is also same thing. Any way you can do it, it's up to you. Okay. Next question is, what is our 2 or more, but less than 5 policies? 2 or more. So between 2, 3, and 4. 2, 3, and so 2 to 5, if I put, I'll get the answer. 2 to 5. 0 event, 1, 2, 3, 4, 5. Right? So if I put 2:5, 2 to 5, 5 will not be taken, 2, 3, 4 will be taken. And then you do sum of dot sum. Right? Either way. Okay. Now if I want to plot the Poisson distribution table, I can simply do this. Okay. And right. Similarly, I can put calculate the Poisson dot CDF, the cumulative distribution also, just like we had for binomial. Very simple. Okay. All right. Okay, let's take another example now. Computing panel probabilities for service at a fast food restaurant. Okay. Accuracy in taking orders at a drive-through window is important for fast food chains. Periodically, QSR magazine publishes the drive-through performance study order accuracy that measures the percentage of orders that are filled correctly. In a recent month, the percentage of orders filled correctly at Wendy's was approximately 86.8%. Right. So in US, probably in foreign countries, you might have seen drive-through through orders where they have fast food driveway, and there is a left-hand side, there'll be a window, and they order something and they take it. It's a takeaway basically order, right? So those accuracy of, because it happens so fast that the accuracy is not always 100% of jotting down the order. So it's around 86.8%. Suppose that you go to drive-through window at Wendy's place and place an order. 2 friends of yours independently place orders at a drive-through window at the same Wendy's. What are the probabilities that all 3, none of the 3, or at least 2 of the 3 orders will be filled correctly? Total kitna trials hai? 10. 3 trials, n is equal to 3. What's the probability that will be filled correctly? And that is also here also, it is the accuracy. Accuracy is what? For correctness, not error. So it will be p-value will be 86.8. The probability of success will be 86.8, which is 0.868. Now what they are saying that all three will be filled correctly, means PMF of 3, n. They see here I'm directly putting the value 3 to get the probability with respect to event, which is 3. Okay, I think I have made a mistake because I have not done this n value. That is it, right? Now calculating the probability that none will be filled correctly. None will be filled correctly means k will be 0. So I can put in 0. This will again be ST because I've imported stats as ST, 0.2%. Calculating the probability that at least 2 will be filled correctly. At least 2. Total number of trials kitna hai? 10. At least 2 means what? 2 and 3. So 2, 3. Done. That's it. So these are my respective probabilities: 65%, 0.2%, and 95%. Or I could have done like this also. I'll calculate all the probabilities with respect to all the events. So kya hoga? Range of what will be 0, 4. That's it. Now if this is my probs, okay, you can specify separately as k is equal to range of n plus 1, right? Now this will be k, right? Now the first question is calculating probability that all will be filled correctly. All will be filled correctly. This will be what? Probs of the last event 0, 1, 2, 3. Just all be filled correctly, or I can make it as 3 also. No problem. Next is what? None will be filled correctly. This will be 0. Right? Next is what? Probability that at least 2 will be filled correctly. At least 2 will be filled correctly. In that case, at least 2 will be 2 is to 4 dot sum. That's it. Either way you can do it. Either you put everything here and then keep on slicing it, or you can directly put that number of events which is expected. Either way, whichever is simple for you. Okay. All right, guys. Then thank you for your patience. All right, guys. Then that is all for today. I hope you are learning, guys. And these things are very important because it simply bridges the gap between what we have learned in the theoretical classes and what how it is actually applied in the corporate world and real world to solve real world problems. Right. I hope you guys are enjoying practicing as well. Stay tuned. I'll see you in the next video.